Good evening, everyone. Before we begin today's talk, I would like to take a moment to dedicate this evening to the memory of Professor Jayant Vishnu Narlikar, a towering figure in Indian science who inspired an entire generation of young minds, many generations actually, but especially those of us who grew up in the 90s. It's special. His passing has felt deeply personal. Through Brahman, the universe, and his tireless outreach, he became more than a scientist, he became our teacher. Personally, I felt like someone very close to me, actually. And so today we remember him with profound respect and gratitude. His demise has hit many of us very personally. So now, welcome to the 19th talk of this year's CASILab Saturday Lecture Series. CASILab, the Center for Advanced Studies and Innovation Laboratory, is committed to demonstration-based science education, research, and innovation. It continues to be a platform where institutional, independent, and grassroots researchers can pursue meaningful scientific work. This initiative was founded by my teachers, Dr. Tushar Kantide and Dr. Shurujit Singh, whose lifelong dedication to advancing physics in this region has inspired generations of students and researchers, including myself. Today's lecture is special for us at CASILab. Our speaker, Arindam Roy, is not only a young and promising PhD scholar at NIT Silchar, working under Dr. P. Srinivasan in the field of nonlinear optics, but also a core member of CASILab. He has worked tirelessly behind the scenes to keep this center active and vibrant, and we are proud to have him on this platform. Arindam completed his BSc in physics from GC College Silchar and his master's in physics from Assam University Silchar. What I could gather from his scholar profile, actually, and correct me if I'm wrong, Arindam's research focuses on the synthesis and characterization of semi-organic single crystals and their applications in nonlinear optics. Despite being early in his research career, Arindam has already contributed to several peer-reviewed publications and was recently awarded Best Oral Presentation at the International Conference on Advances in Materials Science held at St. Dominic's College, Kerala, a well-deserved recognition of his growing potential. Today he will speak on physicochemical property of semi-organic single crystal and its application in NLO, a topic that connects material science, optics, and potential real-world applications. Let us warmly welcome Arindam Roy. Arindam, the platform is yours.
Thank you so much. Uh, mm, I thank you, Shurajit sir and Tushar sir, for giving me the opportunity to present my research work, what I am doing since 3.5 years. And let us start. And thank you everybody for supporting me in this in this work in the CASILab. So I'm starting my presentation. Sir, shall I start? Um, is it visible slide? Okay. So, good evening. Myself, Arindam Roy, and today we will discuss about the physico-chemical property on semi-organic crystal and its application in nonlinear optics. First of all, we need to understand what is single crystals. So single crystals are highly ordered arrangement of atoms on molecules which exhibit structural and chemical stability and also having exceptional transparency in the broad range of electromagnetic spectrum. Also, the single crystals are highly mechanical and thermally stable. And also, in the synthesis process, while making the single crystal, we can tailor to get more advanced application like nonlinear optics, optical application, scintillator, and many other applications. Now moving into the nonlinear optics. Moving into the nonlinear optics refers to the class of phenomenon that occurs with the response to the material when it is incident with the electromagnetic radiation. Basically, as we know in linear optics, we have the polarization of light. The polarization induced in the material is directly proportional for the to the electric field of the light, which is in case of linear optics. But in case of non-linear optics, the polarization induced in the material is not directly proportional to the applied electric field of the light. It can be square of the electric field, it can be cube of the electric field, and so on. This nonlinearity enables unique phenomena such as frequency doubling, self-focusing, optical filters, optical modulators, etc., which are very foundation to the advanced application like ultra-fast switching, high-frequency laser generation, and optical communication. So then there are various nonlinear optical processes. First is second harmonic generation. In this case, when a laser light is incident on a material, the two photons of the same frequency combined inside a nonlinear medium, inside that nonlinear medium single crystal, to form a new photon with twice of the frequency of the original one. And in the third harmonic generation, the in third harmonic generation, three photons of the same frequency interact simultaneously to produce a new photon with three times of the original frequency. So other nonlinear effects are optical Kerr effect. In this case, the refractive index of the material changes with the intensity of the laser light. Four-wave mixing. This occurs when two or more frequencies interact to generate new frequencies. Stimulated Raman scattering. This is a process where incident photon transfers energy to molecular vibration producing frequency shifted light. And optical bistability. This is a condition where a material can exist in two different optical states under the same input conditions. It forms the basis of optical memory, or you can say logic gates. Now, traditionally, how analog materials are formed. Now, traditionally, analog materials started with the pure inorganic crystal like potassium dihydrogen phosphate, potassium phosphate, and BBO. This crystal offer high damage threshold and structural stability, but often fall short in terms of non-linearity. On the other hand, purely organic crystals provide superior nonlinearity due to the delocalized pi electrons in case of organic crystals, but they lack mechanical stability and thermal stability. So there are many properties which we need to understand while making an organic crystal as well as inorganic crystals. So in case of transparency range, organic crystals are narrower, visible to near infrared, and inorganic crystals are wider, UV visible to near infrared. But optical damage is lower, so we cannot use high power laser, high intense laser for the organic crystal, whereas we can use high power laser or high intense laser for the inorganic crystal. So if we use high power and high intense laser, so temperature effect comes into play. So melting point is lower for the organic crystal, and for inorganic crystal it is much higher, as well as the mechanical strength is weaker in the organic crystal, and for inorganic crystal that is stronger. Non-linear, but in case of non-linear response, the organic crystals are higher and inorganic crystals are lower. So taking all the advantages, so such that nonlinear response in terms of the organic crystal, transparency range, optical damage, melting point, and mechanical strength in terms of the inorganic range, we get a semi-organic crystals in which we see that all the advantages of organic and inorganic crystals are present in this case. So it is going to the research of the semi-organic crystals is far better than the organic and inorganic crystals. Now there are various methods for the growing crystals. Let us begin with slow evaporation. It is a classic and widely used technique, especially in the domain of semi-organic crystals as well as in the organic crystals. In this method, the solution containing the desired compound is left undisturbed. Now what happens is that we make a solution and we kept undisturbed for a longer period of time at room temperature, and over the time the solvent evaporates slowly, leading to the supersaturation solution and subsequent crystal formation. There is a big advantage because it is a low cost. Only a beaker and the simple magnetic stirrer is needed. It operates at the room temperature, and quality of crystal is also high with good morphology and optical clarity. But one limitation is that it is very time consuming. I have done my research in the slow evaporation technique. All the crystals what I have grown, that is of 65 days, 70 days, 90 days, like this we have got the resultant crystals. So this is very time consuming. Next method is slow cooling method, in which where hot saturated solution is gradually cooled, causing solubility to decrease and crystal to form. Now advantages is it offer better control over the size, high purity of the crystal, as solute molecules slowly arrange themselves into the lattice. Now limitation is that it need precise control of temperature. If any deflection is there, we can get multinucleation and crystal cannot be formed. Next is the hydrothermal synthesis, a technique employed under the high pressure and the high temperature within a sealed autoclave, and it advantage are it allows very high precise quality of crystals and enables crystallization of low solubility in case of the inorganic crystals. Next is the melt growth technique, which is commonly used in the semiconductor manufacturing. The main two methods are Bridgman technique and Czochralski technique. It operates at very high temperature and it produces the large size crystal and supports rapid growth. This is the comparison between the crystal growth techniques, and now we need to know what are the factors affecting the crystal quality. The first major factor is the temperature. Crystal growth is a delicate thermodynamic process. Fluctuation in the temperature can introduce multinucleation growth. For getting a single crystal, we need a single nucleation process. Single nucleation process means the solution is kept undisturbed and supersaturation is take place. So one molecule will be getting attached to the other molecule and forms a chain of the molecule, therefore forming a good quality crystal. Now if the multinucleation happened, the polycrystalline or polymorph will form inside the crystal. So we do not want that this type of crystals. So also we can get much more defects which significantly affect the physical and optical properties. So maintaining a temperature is a very 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 difficult task, to obtain a stable temperature. Any 1 degree or 2 degree drift, temperature drift, can lead to the completely different crystal structure and habitat. Now next is the choice of the solvent. Solvent are not just passive media, they actively influence the crystal habitat, surface morphology. Different solvents interact differently with the solute molecules and affecting the nucleation and growth kinetics. For example, polar solvents like water favor ionic compounds, while organic solvents like methanol, acetone may be better for studying the organic as well as the semi-organic crystals. Same compound can be yield entirely different crystals depending on the solvent used. What are the components we are using, acids we are using? This is very much factored in the choice of the solvent. Now, mechanical disturbance. So if we disturb it, earlier I have told the solution should be kept undisturbed for a longer period of time. So if the solution is disturbed, again the multinucleation can take place, and hence we cannot get good quality of crystal, and hence also we can get defects inside the crystal. Now, crystal growth is a time sensitive also process. Grow too fast and molecules do not get sufficient time to arrange into the lowest energy or most stable configuration. This results in the vacancies or irregularities in the crystals. Now, growing too slow, the process becomes impractical for scaling or research. The ideal scenario is to find the balance where the growth is slow enough to maintain the structural integrity but fast enough for practical production. Now, optimizing a crystal growth, so we need solvent selection, good solvent selection, temperature control, then the solution preparation, and the evaporation rate control. So these are the four factors we need for getting the for getting a good quality crystals. Now my work is on the base compound, which is known as DEPCO. DEPCO is cage-like bicyclic framework, which is known as 1,4-diazo-bicyclo-2,2-octane, or in short DEPCO, or we can say triethylene diamine in bicyclic form. DEPCO is a cage-like bicyclic framework which has highly symmetry and rigid. Importantly, it has two nitrogen atoms located at the opposite end of the structure. This nitrogen atom serves as a proton acceptor sites, making DEPCO a strong base and an excellent participant in the hydrogen bonding and acid-base reaction. The next critical feature of the DEPCO is protonation mechanism. When exposed to strong acid like nitric acid, sulfuric acid, the DEPCO readily undergoes deprotonation at its nitrogen atoms. This process converts it into a dicatenoic species like DEPCO is to twice positive. Now, what are my research objective? To synthesize a new crystal using a DEPCO as a base and analyze the structure and then evaluate the analog properties of the single crystal. Now, crystal growth methodology. I have used low evaporation solution technique. So, 1,4-diazo-bicyclo-2,2-octane DEPCO is mixed with in solvent, water, and methanol, followed by the addition of silver nitrate and added with the nitric acid. Then it is stirred continuously using an immersible magnetic stirrer at room temperature, and then we filtered the solution and kept it undisturbed for a longer period of time to take the supersaturation and take the nucleation and get the good quality single crystals. So this is the chemical reaction we got. DEPCO is 6H12N2 with silver nitrate and nitric acid, and the solvents are used in methanol and water, and the product we got is C6H14Ag and 509. The full name is 1,4-diazo-2,2-octane 1,4-diamptis nitrato-silver, which in short we gave the name DTNS. So this is the DTNS crystal we got after the slow evaporation process over a 60 days. We got this crystal over a 60 days. As you can see, this is much big in length. So we can say that from slow evaporation process we can get good quality crystals. Now we got to the experimental analysis. We got EDS, then single crystal XRD, FTIR spectroscopy, and then we did UV visible spectroscopy. Now, in first of all, we did EDS because we want to know the what are the elemental composition. Here we got carbon 27.61%. In nitrogen, we got 35.94%. Oxygen, we got 32.18%, and silver 4.26%. As you can see in the figure also, what are the peak related to the elemental composition. Now let us go to the single crystal XRD. So single crystal XRD we have tested in the IIT Madras at room temperature, that is 298 Kelvin, and we have used Shellx 2014 and Platon software to to get the single crystal analysis. So single crystal analysis, we got the crystal system is trigonal. The space group is P3C1, and the lattice parameter is A equal to B is equal to 17.0044 Armstrong, and the C is 7.358 Armstrong. And this crystal structure is available in the CSD file with the CCDC deposition number 2352715. So those are crystallographer. Those we get the new crystal, we need to upload into the CCDC for communicating further about our research work, and as well as the publishing our research work. So this is the chemical diagram of the DTNS crystal. Here you can see the bicyclo or the 1,4-diazo bicycloetene with a surrounded by AgNO3 thrice. We surrounded by AgNO3 thrice. Now role of the DEPCO in the crystal formation. So as we know, the DEPCO's critical feature is the protonation mechanism. The protonated DEPCO molecules stabilize the entire structure, accommodating the silver nitrate cluster in a specially ordered fashion. It rigidly maintains the crystal structure, ensuring that the lattice does not collapse or deform. At the same time, nitrogen centers continue to participate in the hydrogen bonding, which enhances a three-dimensional integrity of the crystal. These intermolecular interactions are hydrogen bonding, and which create a network that is crucial for the crystal's mechanical strength and thermal stability. Now what is the role of the silver in that case? So that is the role of the silver in that case. Here you can see the Ag1, Ag2, and Ag3. The silver oxygen bonding length structure between is about 2.3 to 2.4, reflecting strong ionic and partially covalent interaction. This bond distance are clear indication that silver does not merely shield ideally, it actively participates in anchoring the crystal framework. Additionally, the geometrical arrangement around the silver displays threefold rotational symmetry. The P3C1, 3 is the rotational symmetry combined with the vertical mirror plane. The level of symmetry is critical. It contributes to the non-centrosymmetric nature of the DTNS crystal. So next we need analysis in the FTIR. So as you can see, this is the FTIR graph, transmitted versus wave number. The twin peak at 3121 and 3048 per centimeter indicates the presence of NH stretching frequency, as shown in the earlier figure structure. At peak position at 2796 and 1477 per centimeter indicates the symmetric and bending vibration of NH positive, which can be seen from the structure complex. Also, the peak position of 1433 per centimeter is due to the symmetric stretching of the CH bond. The peak position of 1297 Peak position of 1297 is due to the CN vibration in the complex. The peak position of also 10428893 per centimeter is due to the attributed to the silver oxygen bonding, and peak at 1191 per centimeter is due to the nitrogen oxygen stretching. Next, we come to the UV visible spectroscopy. This figure depicts the optical absorption of the DTNS single crystal. The compound exhibits low absorbance in the visible region. This results also gives the opportunity in the field of nonlinear optics of the DTNS crystal in the range of 350 to 700 nanometer, where the transparency is very high. Sorry, 450 to 700 nanometer, where the transparency is very high. The lower cutoff region is about 450 nanometer, and the low absorption window exists in the visible region, and the highest transparency of the DTNS is about 69%. This plays a great role in the nonlinear optics. Now, if we calculate the band gap by extrapolating, if we create the band gap by extrapolating the data of the linear part of the graph near the transmission edge to the energy axis, we get, so this is the figure, so we get 3.3 electron volt as a band gap, which is very good for the photonic and optical applications. Now next is the thermal analysis. Thermal analysis was carried out between 40 degree and 760 degrees Celsius at a heating rate of 20 degree Celsius per minute in a nitrogen environment. There are around 4.9 milligram in the sample. As you can see in the figure, that TG curve indicates the initial background, which is attributed to the loss of nitrate ions and the creation of silver nitrate clusters that take place between the 180 degrees Celsius to 235 degrees Celsius 235 degrees Celsius, and two distinct endothermic peaks are observed at 180 degrees Celsius as well as in the 194 degrees Celsius, in the DSC curve. In this event, for this we can say that we cannot use this make this crystal using the melt growth technique such as Bridgman technique or Choklatsky technique. So next is the Z-scan analysis. So Z-scan is used to determine the third order susceptibility. As we know, the polarization is if the polarization is directly proportional to the cube of the electric field, so P is equal to epsilon naught chi into E. So chi is the cube of the electric field, so we write chi 3. So this is the third order susceptibility, and Z-scan analysis is used to determine the third order susceptibility. So there are two methods. One is open aperture method, another is closed aperture method. In case of open aperture, pulse laser is focused on the material, and we put a lens in front of the detector to determine the transmitted light. And from open aperture, we can get the nonlinear absorption coefficient. And in closed aperture, a slit is introduced in front of the detector to allow only small amount of light is reach into the sample. This configuration helps to determine the nonlinear refractive index. As you can see, this is the open aperture graph, and from there we calculated, from the graph we calculated beta. Beta is equal to 1.84 into 10 to the power minus 4 meter per watt square. That is the nonlinear absorption coefficient. And from closed aperture, we calculated the refractive index, which is 5.36 into 10 to the power minus 11. Now, if we compare with the other nonlinear optical materials, which is the potassium dihydrogen phosphate, potassium dihydrogen KDP crystal, which is 3.72 into 10 to the power minus 14. Ammonium dihydrogen phosphate, which is 1.81 into 10 to the minus 14, where we got the third order nonlinear susceptibility DTNS, which is 7.603 into 10 to the power minus 8, which is very good in argument with the commercially available KDP crystal. KDP crystal. This indicates that the DTNS has superior nonlinear optical properties, making it promising for various optical applications. Now, what is the significance of the third harmonic generation? Three photons of same frequency combine to generate a new photon, which is the thrice of the frequency of the original photon. This this is very crucial in the field of photonics and the optoelectronics purpose. So the third harmonic generation can be applied to the non-centrosymmetric crystal as well as the centrosymmetric crystal, and makes it particularly valuable for the application requiring frequency conversion and signal processing. Now, what are the future research? What are the future research direction? Structure, we can do the structural modification by adding more multi-metal or different types of metal or different types of acids. In this case, we have used silver nitrate and the nitric acid, where we can use any other metals or acids to get more advantageous crystal. So growth optimization, we can use other method here in place of slow evaporation solution technique, and we can use for the all other purposes like optical detector, optical optoelectronics, etc. So what potential application of DTNS frequency? We can use the frequency conversion, which is thrice omega, which is omega to thrice omega. Sensing of application, optical switching. We can ultrafast optical switching application and other photonics device, because the band gap is very suitable, which is about 3.3 electron volt. So challenges in the semi-organic crystal, growth quality, high quality crystals, because we have to do multiple time recrystallization. Organic crystal or inorganic, we do not need to do multiple times recrystallization, but in semi-organic crystal, for getting a transparent crystal, we need to do many times or 3 to 4 times recrystallization process. Then stability constants, that means the temperature, we need to see also the temperature variant, because the melting point is about 180 to 194, so which is very close. And also semi-organic into the optical system devices present challenges related to the interface compatibility and mounting techniques along the long-term durability. Thank you. This is the first paper, which is also published in the Crystal Research Technology, and I have presented this paper. My co-authors are Dr. P. Srinivasan, which is my guide, Dr. Shegondindu Debray, is also Department of Chemistry from the NIT Silchar, and Shorodip Bakshi, who was a MSc student doing research project under Dr. P. Srinivasan. Thank you and have a nice day.
Hello, am I audible?
Yes, sir.
Hello. Anji, actually, my question is regarding the space group. Could you please open that slide? Yeah, that's right. Actually, as you mentioned that this is the space group P3C1. So have you, go through with the foolproof software, or how you can say that this is the space group of PC31?
Actually, we use actually we give crystals, the new complex crystal to the IIT Madras. They give whole result of the structural determination using the Shelex and Platon software, and they have other software which you use while doing the single crystal analysis. The foolproof software is, I think, for the powder XRD. We use only the single crystal XRD. From there, they give the all the results. What is the crystal system? What are the space group? What are the lattice parameters and other things?
Okay, okay. What is the software name?
Platon software and Shelex software, and they
Okay,
have other software which is paid version which comes with the instrument.
okay, 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 okay. Thank you for the information.
Arindam, have you studied any optical properties of these things?
Only, sir, that Z-scan property, Z-scan, the nonlinear optical properties, not linear
Yeah.
optical properties are only the UV visible. UV visible we have studied. So what is the transparency of the crystal? What is the optical band gap? In which the crystal is has a cutoff region. It shows that in 450 nanometer it has a cutoff region. Then it absorbs. Then the light gets absorbed. So in this part of the electromagnetic spectrum, that is 450 to 750, it transfers the light through the crystal. This is the linear optical property. And in Z-scan, we studied the diffractive index. In nonlinear optical property, the diffractive index depends upon the intensity of the light, along with the wavelength of the light. So we use different techniques, Z-scan technique, to find the diffractive index of the material. And the diffractive is about 5.36 into 10 to the minus 11.
So one comparison sheet you've shown compared to other
Yes.
materials. Yeah, this one.
Yes, this is not refractive index. This is the third order susceptibility.
Chi3.
So which is low, the power of the 10th which is low means which is high, that should get good amount, good quality of nonlinear optical crystals.
Okay.
So KTP is commercially available, and we use in the multiple lasers application. Another is Nd:YAG lasers. We use this is Nd:YAG is also one of the single crystal we use for the laser applications.
So this laser sources what you are using as well as the laser detector. So everything is in your lab.
No, we are building, because our lab is 3 years old. So we are gathering much more. We are gathering
So,
instrument part
so
by part.
suppose this kind of properties, what is the optical properties and other things you are collecting,
We
taking
are
from
sending
IIT Madras.
sample to our collaborators, so that
Okay,
they give us
very nice.
the results.
Okay, okay, okay.
Any other questions? Mm. Yes. Okay. Okay, sir. Yes, I will. I will. include in that slides.
One point I want to understand one thing. Suppose the single crystals which you are growing in your lab, then how will you understand that you have attained your that is objective? How will you attain that you are going to the right track or not? Because as you are developing it, you are taking more than 2 months. You
Yes,
told the
2 months. Actually, sir, what happened? We carefully observed the solution. That's
No,
it is
only by
continuously,
merely by inspection you can. Oh,
merely by
check
inspection,
it.
by seeing the crystal, because we grow crystal like we go too much cases. So by seeing we can understand it is a good quality crystal or bad quality crystal, or the crystal has morphological defects. Defects we cannot tell, because we need to do high resolution XRD. HRXRD we can do, but defects, but we can tell that it will be a good quality crystal or bad quality crystal. So for getting good quality crystal, so what we do, what material through the nucleation process we crush it again and put into the solvent and mix it again and wait for the evaporation. So we repeat the process 3 to 4 times, such that we can get a good and big crystal.
What is the typical size?
A typical size is about, sir, a typical size is about this. I have got highest one. Other crystal I have got only 1 centimeter, point 0.8, then 1.5, like this. This is the highest I've got, about 3 centimeter.
Okay. Thank you.
Thank you, sir.